Assalamualaikum and hi everyone. My name is Nurul Fakir binti Muazzib and my matric number is 227781. So today we will be discussing about radioactive decay and its relation to differential equation. Radioactive decay is a natural process where the unstable nuclei lose their energy by emitting radiation. Over time, the number of radioactive atoms that decreases following exponential pattern. The rate at which a substance decay is proportional to the number of atoms present. So this will give us a differential equation of radioactive decay, which is delta N over delta T equal to negative lambda multiplied by N. So N here is the number of undecayed atoms at time T. Lambda is the decay constants, and also the delta N over delta T is the rate at which the atoms decay over time. Now let's classify the radioactive decay equation based on the types of differential equation. First, they are ordinary differential equation, or we call it as ODE. It is because it only have one independent variable, which is T. And then they are first order differential equation, since the highest derivative is delta N over delta T, so they only have power of 1, so it becomes first order differential equation. Next, they are linear differential equations, since they have no raise in powers, they do not have product, and also non-linear function. And last one, they are homogeneous differential equation, since they are not extra term, or we call it as external function, because it only depends on n. So now let's take a look at the graph that represent the radioactive decay. So here, after resolving the equation of delta N over delta T equal to negative lambda multiplied by N, we will get N equal to N naught multiplied by E to the power of negative lambda multiplied by T. So on this graph, we can see that T, which is time, is on the x-axis, and the number of undecayed atoms is on the y-axis. So as time is increasing, the number of remaining atoms follow the decreasing of exponential curve. This means that the substance is not completely disappears, but the number of undecayed atoms is reducing over time. So this graph shows a direct solving of differential equation that can be related to any real world problem solving.
Assalamualaikum and hi everyone. My name is Nurul Arisha binti Rizwan. My matric number is 228198. So today I'm going to discuss with you guys about differential equation which is involve a pendulum. So let's go to the next slide. And so how do we get the equation of pendulum? So basically, if you can see, we derive it from a top equation, which is, if you can see over here on top of that, T which is equal to IA, which is mean T is a top equation which is equal to negative mg sine theta. For this one, I think you guys have been know this is from the physics one. So, and then R is equal to ml squared. And A which is d squared theta over dt squared, which is mean angular acceleration. So, we're gonna substitute this value, and then we're gonna obtain ml squared d squared theta over dt squared, which is equal to negative mgl sine theta. So how from this we gonna get this equation of differential equation? So then we need to divide this equation with ml squared theta. So when we square this, we're gonna cancel out m for both sides, and L for the left side, we're going to be cancelled out. So the left side, we just going to have dt square over dt square. And the right hand side, we're just going to have g over L sine theta. So we're going to how do you say? We're going to rearrange this equation, and then we're going to get the real differential equation, which is dt square theta over dt square plus g over L sine theta equal to 0. So, what is mean by dt square theta over dt square? It was the angular acceleration, which is mean rate of change of angular velocity. And theta is actually is angle of pendulum. And g is a gravity, and L is length of the string. So over here you guys see there are different kind of length. So yeah, that is L, if you can include this in the L. Okay. So for the last one, we have a classification of this equation. So first one we have this equation is ordinary differential equation. Why is ordinary? Because over here, if you guys can see, we just have only one independent variable, which is mean at here, if you guys see, the dt square is one of the only one independent variable that we have. So that's why it's ordinary differential equation, which also the short form is ODE. So the second one is a second order differential equation. Why was it a second order? Why not one? Okay, if you guys see, and this, we just have only dt square theta over dt square, and it was the highest one. So that's why it was a second order differential equation. For the third one, it was a non-linear differential equation. Why was it a non-linear? It is because the dependent variable and their derivative occur as a product. If you guys see, the sine theta and g over L sine theta is occur as the product, not the right hand side. Okay. So this one. It was a non-linear differential equation. And the last one is a homogeneous differential equation, where it was homogeneous because on the right hand side we just have 0 only. That's why it was homogeneous. That's all. Thank you.
Assalamualaikum and good day everyone. My name is Nur Itifa. My metric number is 230423. So today I will be presenting on the Hooke's law differential equation. Okay, so now let's begin with the basic concept of Hooke's law. So Hooke's law states that the force exerted by a spring is directly proportional to its displacement from equilibrium. So mathematically, it is expressed as F equals to negative kx, where F is the restoring force, k is the spring constant, and x is the displacement from the equilibrium position. So this equation shows that the greater the displacement, the stronger the restoring force acting in the opposite direction. So from Newton's second law, we know that F is equal to m times d squared x over dt squared. So since Hooke's law states that F is equal to negative kx, we equate both expressions so that it will become m times d squared x over dt squared plus kx equals to 0. So in this equation, m is the mass of the object, d squared x over dt squared represents acceleration, t is time, k is the spring constant, and x is the displacement from equilibrium. Now let's classify the differential equation. So firstly, it is a second order differential equation. Why? Because the highest derivative of the equation is the second derivative of x. So this is a second order equation. So next, it is an ordinary differential equation. or ODE because there is only one independent variable, which is time. So this is an ordinary differential equation rather than a partial differential equation. So thirdly, it is a linear differential equation because the dependent variable x and its derivatives appear to the first power with no nonlinear term. Lastly, the equation is homogeneous because there is no external force term on the right-hand side. That is all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh and hello everyone. Today I will be presenting the application of differential equations. Before that, I would like to introduce myself. My name is Muhammad Musikwan and my meeting number is 227579. So let's get started. So this is our topic, the heat equation for temperature. The introductions. So, what is a heat equation? So, the heat equation is a type of a partial differential equation, or we call it a PDE. So, that models heat conduction in materials. This also helps to describe how heat flows through a medium over time. So, these equations is crucial in various fields, including engineering, physics, and environmental science. For example, it is used in electronics to manage cooling, in thermodynamics to study the heat transfer, and also in a climate modeling to understand the temperature changes in the environment. So this is the equations for heat equations, which is delta W over delta T in bracket minus delta square W over delta X square in brackets and equal to 0. So W will be represent of temperature of matter, while T is time, and delta W over delta T is the rate of change of temperature with respect to time. Next is delta square W over delta X square is the second partial derivative of temperature with respect to distance. Moving on the classification of these heat equations. So this equation falls under several classification in a differential equations. Firstly, it was a partial differential equations (PDE) because it involved two independent variables. Secondly, it, it was a second order differential equations because the highest derivative with respect to t is the power of 1, but the highest derivative with respect to x is the power of 2. So that's why it was a second order. And moving on, next, it was a homogeneous differential equation because it is equals to 0. And lastly, it was a linear differential equations. And that's all from me. Thank you.
Hi everyone, my name is Siti Arisha Hanani binti Syed Baharudin. My matrix number is 230632. Today, I'm going to talk about how differential equations explain the motion of a vibrating guitar string and how that vibration turns into sound. For the guitar string, once released, the tension in the string pulls it back to its original position, but due to inertia, it keeps moving and creates waves that travel along the string. This motion is described by a partial differential equation called the wave equation. As you can see in the slide, the equation is the second partial derivative of y with respect to time equals v squared times the second partial derivative of y with respect to x, which is the position. The classification of this equation is second order linear partial differential equation. As you can see in the slide, the degree of the highest derivative is 2. It makes the equations a second order. Next is a linear differential equation because it has independent variables here. and it is a partial differential equation because if you look at this part, it involves more than one independent variable, which is t and x. So how does the guitar make a sound? The string itself doesn't move enough air to produce a loud sound. Instead, the vibration transfers to the guitar body through the bridge, which amplifies the movement and causes the surrounding air to vibrate. Hence, that is how differential equations help to produce sound of the guitar. That's all from me. Thank you.